5 years ago, we celebrated Einstein's discovery of general relativity. This revolutionized our views of space and time. Einstein had already done that once before, 10 years earlier, with his special theory of relativity. What I'd like to do today is to tell you a little bit about these two theories and the strange views of space and time they provided us with. Then I'll jump ahead 100 years and tell you a bit about our current understanding of string theory, which is giving us an even stranger view of space and time. And I'm happy to give this talk today for the Friends of the Goleta Valley Library. Einstein was probably the most famous scientist of the 20th century. In fact, in December 1999, Time magazine named him the person of the century. But what did he really do? Let me start with the notion of an event. An event is simply an occurrence that happens in a small region of space at a definite time. So it's something like a snap of your finger or a clap of your hand. Now, the collection of all events is four-dimensional. That just means that you need four numbers to specify an event. You need to specify the time that it happened, and then the location in space, like by giving the latitude, longitude, and altitude. Einstein is famous for saying that the set of all events forms a four-dimensional continuum. But that's really nothing new. It's just the statement that time is one-dimensional. You need one number to specify the time, and space is three-dimensional. You need three numbers to specify a point in space. Well, Einstein, of course, did do something revolutionary. In fact, he did two things. The first is his special theory of relativity, which had a number of very surprising features. The first is nothing can travel faster than light. You're used to seeing the sign on the left, which requires police to enforce and is frequently violated. But the speed limit on the right doesn't require any law enforcement. It's a law of nature. Nothing can travel faster than 186,000 miles a second, the speed of light. Now that's of course extremely fast, but the important thing is that it's finite. And that means that even if one event happens after another, there's no way, even in principle, to send a signal from one event to that other event. It may not be possible. How do we know that this is true? Well, this speed limit is tested every day in particle accelerators around the world. The highest energy accelerator we have at the moment is the Large Hadron Collider at CERN, located in Geneva, Switzerland. And here, protons are pushed by electric and magnetic forces harder and harder. And as you push them more and more, their speed gets closer and closer to the speed of light, but they never exceed it. At the moment, protons are being pushed to 0.9999999 the speed of light. But the harder you push, just the closer the protons get to traveling at the speed of light. A second strange feature that is given by special relativity is if two events occur at the same time for one person, they will occur at different times for another person in motion relative to the first. In other words, the notion of simultaneity is relative. In fact, you can even have a situation where two people disagree on which of two events occurred first. That can only happen when these two events are situated so that you can't send a signal from one to the other, so there's no violation of causality. But more generally, the elapsed time between two events depends on who is measuring it. It's not just time, but the spatial distance between two events also depends on which person is measuring it. In other words, the length of an object is observer dependent. Now, even though the elapsed time and the spatial separation are both observer dependent, there is one combination of the two that everybody agrees on. There's one well-defined distance between two events. And what this means is that space and time are truly unified into a single entity that we call space-time. Different people will break up space-time into their own notion of time and space, but two observers in relative motion with respect to each other will assign different values to the elapsed time and the spatial separation, spatial distance. A remarkable consequence of this unification of space and time is that the time you experience depends on your state of motion. This is not just a property of mechanical clocks, but applies to biological clocks as well. Your watch runs slower and you actually age less when you're in motion. If you take two watches with you to the track and synchronize them before you start, leave one at the starting line and carry the other one with you as you run around the track, when you come back, in principle, the watch you carried will be slower, will have register an earlier time than the watch you left behind. Of course, we don't see this in everyday life because the effect is tiny unless you're moving close to the speed of light. But this has been tested in many experiments, not with clocks or watches, but with very accurate atomic clocks. You can take two atomic clocks, synchronize them, put one in an airplane, fly it around the Earth, and when it returns, it will no longer register the same time as the one that was left behind. In fact, atomic clocks are so accurate now that they can measure differences even when the relative speed is only something like 25 miles an hour. Another way this has been tested is with elementary particles. So there's a particle known as the kaon, which is unstable and normally lives only for a very short time before it decays into other elementary particles. But when the kaon is created in a particle accelerator and it's moving close to the speed of light, it appears to last much longer because its internal clock is moving more slowly. Now this provides a way to travel into the future. You can board a spaceship and travel close to the speed of light for a year, and when you return, it can be 10 years later on Earth. You will have aged only 2 years, but people on Earth will have aged much more. But this, unfortunately, is a one-way trip. You can travel into the future in special relativity, but there's no way to travel into your past. Now let me turn to Einstein's second revolution, his general theory of relativity. This is a theory of gravity. So the first question we have to answer is, why did we need a new theory of gravity? After all, we had Newton's theory, which worked extremely well, explaining everything from the motion of planets to falling apples. And the reason Einstein wasn't satisfied with Newton's theory is that Newton's theory was incompatible with special relativity. It required that we know the separation between two objects at one moment of time. It required that we know the separate time separation and space separation. But we just saw that special relativity says there is no such thing as absolute simultaneity, and different observers will assign different values to the spatial separation or time separation of two events. So Einstein was driven to find a new theory of gravity which was compatible with special relativity. And he hit upon a radical idea. He realized that we could explain all the phenomenon of gravity by simply imagining that space-time is curved or warped. And he had the idea that matter will cause space-time to stretch or warp, and gravity is nothing but objects responding to this curved space-time. A standard way to picture this is to think of space as a rubber sheet. If you take a heavy object like a bowling ball and put it on a rubber sheet, of course the sheet will bend down. Then if you take a lighter object like a marble and roll it next to the bowling ball, it will be deflected, not because of any special force acting between the bowling ball and the marble, but just because the marble is responding to the local curvature of the sheet that it feels. And this is a model of our solar system. If you think about the bowling ball as being the sun, which is curving the space around us, and the planets are like the marbles, which are in orbit around the sun, just because they're responding to the local curvature of space that they experience. Another consequence of this curvature or warping of space and time is that light is bent by gravity. Light traveling along the straightest possible path actually curves. So a star is, if a star is actually here and the light from the star passes next to our sun, say, it will be bent, and we will see the star as if it was out here. Now, when Einstein first proposed this, the only way possible to observe this effect was to look at stars that were behind the sun and see if they were deflected from where they were when the sun was not in the way. But of course, the sun is very bright, and you don't see stars behind the sun normally. So you had to wait for an eclipse, when the moon blocked out the sun, and you could see the stars that are behind it. There's a funny story about this. In 1911, Einstein was developing his theory of gravity. He didn't have the final form yet, but he realized that light would be bent by gravity, and he wrote a paper making a prediction for the amount that light should be bent. But he didn't have the full theory, and the prediction he made is half of what we now know the true answer to be. There was an eclipse of the sun in 1914, and there was an expedition set out to measure this effect that Einstein had predicted. But fortunately for Einstein, the weather was terrible, and they got no useful data. A year later, in 1915, Einstein finished his theory of general relativity. He calculated this effect again and made the correct prediction, or made his final prediction. And then 4 years later, in 1919, there was another eclipse of the sun, and there was 2 expeditions that were set out, and they got observations in agreement with general relativity, and this confirmation really catapulted Einstein to fame. But you can imagine what would have happened if the 1914 expedition had been successful and gotten an answer which was a factor of 2 different from what Einstein had predicted in 1911. Einstein would have then come out a year later with his final theory and said, oh yes, now I get an answer in agreement with observations, but it wouldn't have had anywhere near the impact that the actual 1919 confirmation had when Einstein had predicted the answer first, and it wasn't just correcting an earlier prediction that he had made. Now, the amount that light is bent depends on how compact an object is. And if the object is compact enough, the light is bent so much that it doesn't escape. And that leads to the idea of a black hole. So to explain how black holes form, let me remind you how stars are born and die. Like everything else, stars don't live forever. They are born when a gas cloud starts to collapse under its gravitational attraction. As it gets smaller, it gets hotter, and eventually the gas gets so hot in the center that nuclear fusion takes place. And then you get a stable object, which is our star. So a star is just a hot ball of gas, which is kept hot because of nuclear fusion taking place in the core. Hydrogen is being converted to helium. The star lasts for a very long time, often billions of years, but eventually all that nuclear fuel runs out. And when it cannot keep itself hot, the star cools down and starts to undergo gravitational collapse. And a sufficiently massive star will undergo complete gravitational collapse until you form a black hole. And the surface of the black hole the region, the sort of beyond which a light can escape, in fact, nothing can escape, that's called the event horizon. Now you have to be close to a black hole to experience this strong gravitational field. If the sun was to turn into a black hole tomorrow, the orbit of the Earth really wouldn't change. Of course, it would get very cold very quickly. Now, another way to say that the gravity is getting strong is to say that space is becoming highly curved. So here's a picture of what space near a black hole looks like, where it's getting more and more warped as you get closer to this event horizon. Now, in addition to black holes formed from stellar collapse, astronomers have found most galaxies have a huge black hole, 1 million to 1 billion times larger than the black holes formed when stars collapse. These supermassive black holes, as they're known, are found in the center of most galaxies. Now, these black holes tend to rotate, and they can power enormous jets. So what's happening is the matter falls in toward the black hole, and then before it enters the black hole, it gets shot out along the axis of rotation of the black hole. And these produce, well, these are believed to be the energy source for the most powerful energetic objects in the universe, such as quasars. Another interesting effect of general relativity is that matter in motion produces ripples in space-time called gravitational waves. So by just shaking my arm, I am producing gravitational waves, of course, a totally minuscule and unobservable amount. To produce significant gravitational waves, you need a massive compact objects moving very quickly. So a great example is the binary orbit of two black holes shown on the picture on the left. So if these objects are these black holes are orbiting around each other, they are producing ripples in space-time, these gravitational waves, which go out. And we now have gravitational wave observatories in the United States and in Europe that are looking for these gravitational wave signals. In the United States, the observatories are called LIGO, for Laser Interferometric Gravitational Wave Observatory. There are two, one in Hanford, Washington, the other in Livingston, Louisiana. And each observatory consists of two 4-kilometer-long arms at right angles to each other. You see the picture of the Livingston, Louisiana site on the right. And to detect a gravitational wave, you hang two masses at one at the far end of this arm and one at the center. And then with lasers, you measure the distance between these two masses very, very accurately. When a gravitational wave hits the Earth, the distance between the objects changes. One arm becomes slightly shorter, the other arm becomes slightly longer, and then just a short time later, it reverses, and it oscillates like that. And so that's how these gravitational waves are supposed to be detected. There's a site called Virgo in Europe, which is similar and also looking for these gravitational waves. Well, on September 14th, 2015, LIGO saw two black holes merge for the first time. Each black hole had a mass about 30 times the mass of the sun. And when they merged, they didn't form a 60 solar mass black hole, but only like a 57 solar mass black hole, because 3 solar masses of energy were radiated away. Now, what that means is you use Einstein's famous equation, E equals mc squared, to convert mass to energy. And we know even tiny amounts of mass produces a lot of energy. That's this nuclear fusion or atomic bombs. In this case, we had 3 times the mass of the sun converted entirely to energy in a very short time. in less than 1/10 of a second. And in fact, that event for this brief moment was brighter than all the stars and all the galaxies in the entire universe. It was quite an amazing event. And on the right, I show you the signal. So what I'm showing is the change in the length of the arm of this gravitational wave detector. We have first the Hanford data showing this oscillation. Then we have the Livingston data. You build 2 detectors because you want to make sure your signal is real and not the result of some truck going down the highway causing some vibration and some shaking of your observatory. You want to get confirmation having the same signal seen in both detectors. And so we have the 2 original signals here, and then we have them combined in the bottom plot. It says it's shifted here because we have to account for the very small time delay. The signal reached one detector 7 milliseconds before the second. And so you have to take that into account when you compare the signals. But after that very slight shift, you see the signals line up extremely well. The thing to note here is the scale. So on this vertical axis is measured the strain. That is simply the change in the length of the arm divided by the original length, which is 4 kilometers. So the units are 10 to the minus 21, which means it's a decimal point, 20 zeros, and then a 1, an extremely tiny amount. And what this corresponds to is these detectors can measure the change in the length to about 1,000th the size of a proton. It is absolutely remarkable that they're achieving that kinds of sensitivity, but that's what you need to detect these gravitational waves because they are very weak by the time they reach us here on Earth. But this signal was detected, and here you see the time, and you see the whole thing happened extremely quickly, that this most of the energy was released in this final burst over here, and that whole thing is in less than 1/10 of a second. So it was just an incredibly dramatic event. These detectors have now been online, well, for almost 5 years. We have on the order of 50 black hole binaries that have been seen through their gravitational waves by now. Just a few weeks ago, it was announced that they had seen the most massive 2 black hole system ever. They had a black hole 85 times the mass of the sun and another black hole 65 times the mass of the sun in orbit, and they saw that orbit decay, the black holes merge, and something like 7 or 8 times the mass of the sun was converted to energy in a very short time. Quite an amazing event. Now let me just show you here a numerical simulation. So this is showing 2 black holes in orbit around each other. This is obtained by solving Einstein's equations from general relativity on a computer. But you can follow the black holes as they orbit, and you see the gravitational waves, these ripples being given off. And what you notice is that as the black holes get closer and closer, they're speeding up, they're orbiting faster, so the frequency of the gravitational wave increases, and also the amplitude, the strength of the gravitational wave increases. So this is like a chirp. It's something where the frequency gets higher and the amplitude gets higher, and it ends up being a chirp. That's the signal of these gravitational waves. So let me turn to another important effect of this curved space-time, and that is that time slows down near a massive object. You actually age more slowly here on Earth than you would out in space. Of course, the effect is tiny. You save maybe 1 second every year. But near a compact object like a black hole, the effect is much greater, and time can almost stand still or appear to stand still. It slows down by an arbitrarily large amount. And that was shown clearly in the movie Interstellar a few years ago, where they showed how time is like a resource when you're traveling near a black hole, which you have to manage carefully. Now that effect of time slowing down not only has been measured, but has practical applications in the global positioning system. So this system, which lets you locate yourself anywhere on Earth, wouldn't work if relativity wasn't taken into account. So what happens in the global positioning system is we have a constellation of satellites orbiting the Earth. Each one is equipped with an accurate atomic clock. And each satellite continuously sends out information about its location and its time. A GPS receiver on Earth collects the signals from at least 4 such satellites. And by just comparing the arrival time and the location information in each of these signals, you can detect or deduce your time, your location on Earth, and in fact, your time as well. Now, there's an interesting story about this. In order for this to work, 2 relativistic effects have to be taken into account. Because these satellites are above the Earth, the atomic clocks would run a little bit faster than the time on Earth. But because they're moving, a special relativity effect says they would actually slow down. The combination of those 2 effects is still 1,000 times greater than the accuracy of the atomic clocks. But when these satellites were first launched, the first GPS system was launched in the 1970s, there was some controversy over whether these relativistic effects were really there, had to be taken into account. So they included a switch. They said they could get the data from the satellites, including the relativistic effects or not including the relativistic effects. And within a month of taking data, it was clear that the relativistic effects had to be taken into account. And in fact, they had like a 1% test of general relativity just from these early GPS satellites. Now let me talk about a couple things that you hear about in science fiction. And the first is wormholes. So if space is warped and curved, you can ask, is it possible to have shortcuts? Could you have a situation where to get from a point here to here, you could go through this wormhole, this shortcut, and not have to go all the way around? Well, in general relativity, it turns out that it's very difficult to produce one of these wormholes. Wormholes tend to collapse. Before you can get through, they collapse and form black holes. And so for a long time, people thought wormholes just couldn't exist in general relativity. There was no traversable wormhole. If you ever tried to get through one of these wormholes, you would end up inside a black hole, and then you couldn't get out. But surprisingly, in the last few years, it's been discovered that wormholes actually can exist. Traversable wormholes can exist, but it will always take you longer to go through than to go around. So that's the catch. You can get wormholes which stay open long enough for you to go through, but time slows down when you go through. So it actually, it would be faster for you just to go around and you come out here on the other side. It would be quicker for you to go around a long way. So it's not a shortcut. These wormholes, the traversable wormholes exist, but they really don't provide shortcuts. What about time machines? Well, time machines probably don't exist in general relativity. And notice I say probably. It turns out to be surprisingly difficult to prove that you can't build a time machine in general relativity. There are, in fact, space-times in general relativity which describe time travel. There are solutions of Einstein's equation in which you can travel into your past. But these time machines have always existed. It's very difficult to build a time machine. So if you have no time machines now and you want to build something that will produce these, be able to go into your past and the future, there are lots of problems. And I believe most people today think it is not possible to build a time machine in general relativity. Now let me say a few words about cosmology. So this is the study of the universe as a whole. And when we look out into space, what we see are that distant galaxies are all moving apart. The universe is expanding. But it's important to understand what this means. This means that the distance between galaxies is getting bigger. The individual galaxies are not getting bigger. The Earth isn't getting bigger, and you are not getting bigger. At least if you are, you can't blame it on general relativity. So going back into the past, all these galaxies must have been closer together. And general relativity tells us that 13.8 billion years ago, all the matter in the universe was squeezed to an essentially infinite density, an event known as the Big Bang. Now, it's important to realize the Big Bang is not like an explosion at one point in space. The galaxies are approximately uniformly spread out over all space, and there is no center. So we are not the center of the universe when we see galaxies moving away from us. Every galaxy will see other galaxies moving away from them. The distance between any two galaxies goes to zero at the Big Bang. So the Big Bang is really something that occurred everywhere at the same time. A natural question is what happened before the Big Bang? Well, according to general relativity, this question is meaningless. Time itself begins at the Big Bang. And if there is no time, nothing can happen. Well, that's not completely satisfying. And in fact, we don't believe it's the final answer. Because the Big Bang, and in fact the center of black holes, are both examples of singularities. These are regions of infinite gravitational field. Space and time end at singularities. But general relativity itself breaks down there. And we believe that it must be replaced by another theory which includes quantum theory. Quantum theory was the other big revolution in physics in the 20th century. And general relativity doesn't incorporate the ideas of quantum mechanics. And so we need a theory which does, something called a quantum theory of gravity. So we have the following picture. We're looking for a theory that reduces to both general relativity and quantum theory as we know it in suitable limits, but also combines their principles and will give us a theory of quantum gravity that is also consistent with quantum mechanics, which describes, I should say, quantum theory is necessary for describing very small objects like atoms and elementary particles. Well, the best understood theory of quantum gravity that we have today is string theory. So I'm now going to turn to that. And the first question we should ask is, what is string theory? And unfortunately, I can't give you a simple answer because string theory is still being developed. It has many facets, and in fact, I sometimes feel like one of those blind men in the famous story of the blind man and the elephant. The blind man that's looking at the tail describes the elephant like a rope. The one looking at a leg thinks it's more like a tree. Everyone comes to a different description because they're looking at only a small part of the whole picture. And string theory is a bit like that. It's an enormous structure. We know pieces of the story, but we don't have a good, complete grasp of it yet. But let me tell you a bit about these pieces that we have understood. But first, I should say, why are we studying string theory? It's in fact the promising candidate for both a theory combining the principles of general relativity and quantum theory, as I said, this quantum theory of gravity. But it's also of interest because it provides a unified theory of all forces and particles. And so let me first say a word about this unification. Well, as you know, molecules are made up of atoms. The atom itself is made up of a nucleus and electrons. The nucleus is made up of protons and neutrons, and each of them are made up of even smaller quantities, which we call quarks. The idea of string theory is that these smallest quantities that we know, the electrons and the quarks, are themselves made up of strings. They are, in fact, excitations of a single object, which is the string. The string can vibrate in different ways, and that gives rise to these different kinds of particles that we have seen. String theory also has a very simple picture of interactions. We know that a single string can split into two, or two strings can combine into one. And the remarkable thing is that this simple geometric interaction reproduces all the known forces. And string theory in particular reduces to general relativity in a certain, in a suitable limit. So I don't have time to tell you a lot about string theory, but I want to focus on what it says about space and time. So string theory predicts that space has more than 3 dimensions. It may have 9 or even 10 spatial dimensions. And remember that all this means is that it takes 9 or 10 numbers to specify a point. But you might say, you know, we see the 3 dimensions, the familiar 3 dimensions. Where are all these others? Well, it's not that they're out in space somewhere. They're everywhere, even right near you. So why can't we see them? Well, the standard explanation is that these extra dimensions might be curled up into very tiny circles. So what you see here from a distance looks like a one-dimensional line, but when you look closely, you'll see it's a very, very thin cylinder. So it actually is a 2-dimensional object with a very, very small circle and a very long length. And the idea is that the long length is like the 3 dimensions we see, and the tiny circle is like all those extra dimensions that we don't see. And if these dimensions are very small, it would be very hard to detect in any experiment that we have done. It would take, in particular, a lot of energy to probe these very, very tiny extra dimensions. And although the extra dimensions are small, they don't have to just be circles. The extra dimensions can have many different shapes, and this affects the type of particles that we see, since strings oscillate in these extra dimensions, as well as in the 3 big dimensions that we see. So let me turn to a different side of the elephant now. I'll give you another aspect of string theory. When string theory was first being developed in the 1980s, people asked, what's so special about one-dimensional objects? Why don't we have 2-dimensional objects and like membranes? And it turns out that string theory does include these objects. It's not just a theory of strings. There are higher dimensional objects which we call branes. And this name comes from the word membrane, but in fact, since we have a total of 9 or 10 spatial dimensions, we can have these membrane-like objects, these branes, which are 2-dimensional, 3-dimensional, 4-dimensional, etc. These branes are much heavier than strings, so they were not noticed until the 1990s, but they have important consequences. And for our purpose, one important consequence is that the extra dimensions might actually be large, but we don't see them because we live on a 3-dimensional brane in this bigger space. So the picture here is that the total space time or space of string theory is big. It has all these extra dimensions, but there are these 3-dimensional objects, which are the branes, and we could be forced to live on the brane. And the way that happens is that in string theory, we have not only these closed strings, which are like loops or circles, but there are open strings. There are strings with two endpoints, and those endpoints are forced to lie on the brain. And so if the string can only move along the brain, it's stuck on the brain, and excitations of those strings can represent all the particles that we've seen. Things that are off the brain would only be detected through gravity, because gravity is curvature of space and the space exists everywhere. But if in fact we are living on one of these brains, there could be another brain, something that could be thought of as a parallel universe. And objects on this brain could be detected on our brain only through their gravitational effects. So this is something which is sometimes called brain worlds, but it's another way in which we can deal with these extra spatial dimensions in string theory. And finally, let me turn to yet another view of string theory, another side of the elephant. Under certain conditions, there is a dual description of string theory, which does not include any strings or brains, or even any gravity. Yes, it is completely equivalent to the original string theory. And both strings and gravity emerge from something else. The new description is not more fundamental, just equivalent. So this duality is something like this. This is a standard illusion where you can either see a white vase or two black faces. Each description is a complete description of the picture. The descriptions sound very different, but they are describing the same object. So in string theory, we have this duality to a different description. It's the same physics, the same structure. We can describe it as strings or brains, or we can describe it in terms of a completely non-gravitational theory. It's quite surprising, quite remarkable, and it is something which has come out of studies of string theory. But it's even stranger than it sounds, because this dual description lives in a lower dimensional space than the original string theory. The entire higher dimensional string theory can be described by a non-gravitational theory in only two spatial dimensions. So this is reminiscent of a hologram, where you have a two-dimensional image or two-dimensional picture, which you look at it and it looks three-dimensional. Well, here we have a theory in two dimensions, which is somehow reproducing all of string theory with its higher, 9 or 10 spatial dimensions. And this correspondence, this duality, is called holographic because of this remarkable property. Well, what is the evidence for this duality? In fact, there are by now an enormous number of calculations which can be done on the two sides. In other words, there's one physical quantity which you calculate using the usual tools of string theory, or you can calculate it in this dual description in a non-gravitational theory with no strings, but just translate the problem into that language and you can do the calculation there. The calculations look totally different, but when you compare the final answer, they completely agree. So I should say we don't have a proof of this duality, the proof of this equivalence, but after you've seen enough of these type of checks, you start to believe that it's really there. Okay, well, let me summarize. We've seen that special relativity taught us that space and time are unified. General relativity taught us that space and time are curved or warped. And now we've seen that string theory is teaching us that space can have many more than 3 dimensions, but many of these dimensions can emerge from a theory in only 2 spatial dimensions. And I will stop there.